of it. Yeah. Okay. Yeah. So lecture. Yeah. So today we will get to the proof of Jordan form. Yeah. So last time we discussed some notion of exponent of a generalized eigenvector. Yeah. So let me recollect that. So phi is a linear operator on a finite dimensional vector space V. Then V lambda is basically all V in V such that some power of phi minus lambda I kills V. Yeah. And we know that the non-zero elements of V lambda are precisely the generalized lambda eigenvectors. No? So if we take a non-zero element of V lambda, then we say that n is an exponent of V if phi minus lambda I power n is 0, but no smaller power is 0. Yeah. So in particular, phi minus lambda I power n minus 1 should be non-zero. Then of course the other smaller powers can't be 0 as well. Yeah. So it's the least n such that phi minus lambda I power n V is 0. Okay. So that is the exponent of n. Maybe I can underline this. Okay. So this is what I claimed last time, and I gave proof of half of it. So let's say V lambda small v be a element non-zero. Yeah. So be an element of v of exponent n. So in particular, it's non-zero. Yeah. And define Vj to be phi minus lambda I power j v for some j. Yeah. Then this is then Vj is of exponent n minus j if j is between 0 and n minus 1. So maybe this is the first claim. Yeah. This is the 0th claim. And then the next claim is that if you consider this set V0, V1, Vn, V0 is same as V because j equals 0 means this is the identity matrix. So V0 is same as V. So if you run through V0, V1 up to Vn minus 1, yeah, up to Vn minus 1, you'll get non-zero, guys, because V is of exponent n. And if you try to do Vn, then that is already 0. Yeah. So it's saying that if you consider these vectors, then this is linearly independent. And if you consider the subspace generated by W, then phi restricted to W is an invariant so then W is an invariant subspace. So maybe is phi invariant subspace, and so maybe we'll prove this first, and then the matrix of phi restricted to W is going to be this thing. Yeah. So this part more, I mean, invariant, and this part we more or less proved. Yeah. So in fact, we saw that this formula holds. Phi of Vi is Vi plus lambda Vi minus 1. And Vn minus 1 is of exponent 1. Yeah. So lambda, so it's actually an eigenvector. So phi of Vn minus 1 is lambda Vn minus 1. Okay. So this is the first result for today. And then we'll do more. Okay, so first let's see. I mean, it is clear that Vj is a generalized eigenvector, and let's see that its exponent is also n minus j. So this is just one line, yeah. So if you apply phi minus lambda I power n minus j to Vj, well, Vj is phi minus lambda I power j, yeah, of V. So if you multiply this through, you get phi minus lambda I power n V is 0, yeah. So it can have exponent n minus j because some power is n minus jth power when you apply phi minus lambda I, then it becomes 0. And if you apply one less, then you get phi minus lambda I power n minus 1 v, which of course is non-zero because v has exponent n. Yeah. So if you apply phi minus lambda I power n minus 1, then it can't be 0. Is that okay? Are you guys still with me? Because somehow things are not visible. Your screen is, I mean, your video is not visible to me. So I'm not sure if you guys are with me. Oh, yeah. Okay. So I don't know what is going wrong, why it is stopping all the time. Can you guys hear me now?
Yes, sir.
Okay. So is this so you will have to communicate better, right? Because we are getting disconnected. So if I ask you, is this clear? Then some of you should respond. Yeah. So is this okay now that Vj is has exponent n minus j? That part is clear.
Yes, sir. Yes.
Okay, good. So Vj has exponent n minus j. Now we want to prove that this is a linearly independent set. Yeah. This V0 to Vn minus 1 is a linearly independent set. So we will do by induction and we will start from the rightmost vector. Yeah. So we know that Vn minus 1 is linearly independent because it is non-zero. Yeah, it's an eigenvector. In fact, it's an eigenvector. We know that Vn minus 1 is non-zero because it has exponent 1. It's an eigenvector. So, so it is linearly independent. Now suppose you collect the right n minus j terms. Yeah, so j, vj plus 1. Suppose this is linearly independent. Yeah, for some j greater equal 1. Then we will show that if you adjoin vj minus 1 as well, then also it stays linearly independent. So if you prove that, then you can apply induction and you get that the whole list is linearly independent. Yeah, is that okay?
Yes.
Yeah.
Yes, sir.
Yeah, good. So now consider this linear combination. So we want to say that if we adjoin Bj minus 1, then it stays linearly independent. So suppose there is some linear relation. Yeah. So you apply, so this linear relation is, maybe I should write AIs. AIs in, um, AI is in, yeah, J is fixed because, yeah, so for some AIs in F, you can find, say, some relation, then we have to show that all these AIs are zero. Yeah. So what you do is apply phi minus lambda I power n minus j to this equation. So what will happen if you apply phi minus lambda I power n minus j to this equation? Yeah, so all the term Vj plus 1, etc. will become 0, right? Because Vj has exponent n minus j, Vj plus 1 has exponent n minus j minus 1, and so on. Yeah. So if so, you know, phi minus lambda I power n minus j will kill Vj plus 1 up to Vn minus 1. Yeah. So if you apply this, then the only thing remaining will be this guy. Yeah. So phi minus lambda I power lambda I power n minus 1 v0, and these things will be 0. Yeah. So that, and this guy is not going. So what you'll get is basically vn minus 1, aj minus 1 times vn minus 1. This is precisely, this is nothing but vn minus 1. Yeah. So so since vn minus 1 is non-zero, you get that aj minus 1 must be 0. Yeah. So since aj minus 1 is 0, now you have the relation only between aj to an minus 1. Yeah. But we have already assumed that vj plus 1 up to vn minus 1 are linearly independent. Yeah. So that tells you that these aj plus 1 and so on must be all 0. So that tells you that 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 this is linearly independent. Yeah. So hence hence so v0 to vn minus 1. So we are done by induction by principle of mathematical induction. Yeah. Okay, so we have proved this first statement that B is indeed a linearly independent set. Okay. And why is W so this I didn't argue, but this should be okay as well, yeah? So why is W a phi invariant subspace? So what happens if we apply phi to W, yeah? So we just have to check what happens we apply phi to the basis elements, yeah? V0 to Vn minus 1 form a basis. So phi of V0 lands in W, right? Because maybe first we apply, actually phi of V0 is V1, not phi of well, phi minus lambda I of V0 is V1. So okay, let's just look at this let's prove this formula, and from this formula we'll get that W is phi invariant subspace, yeah, because phi of Vi for each phi of V0, phi of V1, and so on, up to phi of Vn minus 1 will all lie in W. Yeah. So this formula we already saw. Yeah. So for I between 1 and n minus 2, we know that Vi is just phi minus lambda I of IV. Yeah. This is the definition of Vi. So, but this is we can split it into two factors: phi minus lambda I of times phi minus lambda I for I minus 1 V. Yeah, but the second factor is precisely Vi minus 1. Yeah, so this is Vi minus 1. The second factor by definition. Yeah, and then if you expand it, phi minus lambda I applied to Vi minus 1, that is same as phi of Vi minus 1 minus lambda of Vi minus 1. Yeah, because lambda I is just this thing. So that tells you that phi of Vi minus 1 is Vi plus lambda of Vi minus 1. Lambda times Vi minus 1. Yeah. So that tells you the first line of this equation. And of course, phi of Vn minus 1 is lambda times Vn minus 1 because Vn minus 1 is an eigenvector. Yeah. Right, because I mean, if you apply phi minus lambda I to Vn minus 1, you get 0. Right? It has exponent 1, so you get 0. So that tells you that phi of Vn minus 1 is just lambda times Vn. Is that okay, everyone? Yes. As I said, you have to respond yes or no, then only I can proceed.
Yes, sir.
Yeah. Okay. So so we see that phi of each of the eigenvectors, each of the basis element of W lands in W. So that proves that W is phi invariant subspace. Yeah. So now we can talk about matrix of phi restricted to W with respect to the basis B. Yeah, where B is this basis V0 to Vn minus 1. So of course now you again use these identities. Yeah. So we know that V0 is phi of V0 is V1 plus lambda V0. Yeah. So the diagonal entry has to be lambda, and the one, so it is basically lambda V0 plus V1. So the diagonal entry has to be lambda, and the one below it is going to be 1. So the rows are given by, the columns are given by the coefficients of these things, right? That is how we wrote down the matrices of a linear operator. So this is something which we did in the first few classes. Yeah. Similarly, the other ones. Yeah. Phi of V1 is lambda V1 plus V2. Phi of V2 is lambda V2 plus V3, and so on up to n minus 2. It will be that way, and then at the end stage you just get the last column contains only zeros and one and lambda. There is no one below. Yeah, because there is no Vn. Yeah, Vn is essentially 0. Okay, so this completes the proof of this this part. Is that okay? Yeah, so our Jordan form is coming out to be transpose of what we wrote, but that's not a problem. Yeah, it's just actually if you write this basis vector in the reverse order, then you can check that the Jordan form or the matrix will be in the will be transposed. Yeah, so maybe this is something as an I mean, I can't say it's a homework. This is just an exercise, some observation. Yeah, the matrix of phi restricted to W with respect to the same basis vector, but in the reverse order. If you write it down, then you'll get an upper triangular matrix. Yeah, because see Vn minus 1 is a eigenvector. So the first column should be just lambda. Yeah, and then zeros. Vn minus 2 is lambda times Vn minus 2 plus Vn minus 1. So 1 and then lambda. The coefficient. So if you look at phi Vn minus 2, it is Vn minus 1 plus lambda times Vn minus 2. So that is why you have 1 and lambda and so on. Yeah, so it's not. So you can convince yourself that this is the matrix you will get if you write the basis in the reverse order. Okay. Okay. So yeah, so now I mean let's look at we discussed characteristic polynomial in the proof of that decomposition. So the minimal polynomial has some similar properties. So I didn't want, since I assigned the homework for characteristic polynomial, I thought I'll do something for minimal polynomial. So let the minimal polynomial of phi be this thing, yeah, t minus lambda power n lambda for some n lambda, or n lambda greater equal 1, times gt, where gt doesn't have any factor of t minus lambda. Yeah, so gt does not divide. I have written divides. Yeah, gt. So you take out all the factor of t minus lambda, and whatever remains is gt. Yeah. So say p. Minimal polynomial has this factorization. Yeah. Then the minimal polynomial of phi restricted to this v lambda, the space of generalized eigenvector, is precisely t minus lambda power n lambda. Yeah. So this is the statement for minimal polynomial. Same statement is true for characteristic polynomial as well, which will be the homework problem. So you replace minimal polynomial by characteristic polynomial, you'll have this m lambda here at times gt, and this t minus lambda power m lambda should be the characteristic polynomial. So that I'll assign as a homework for you. But let's see why the minimal polynomial is this. Yeah. So let ft be the minimal polynomial of phi restricted to v lambda. We want to prove that ft is t minus lambda power n lambda. Yeah. So this is not too deep. So maybe I argued last time as well. What happens is some power of t minus lambda will annihilate v. Yeah. When you plug in phi in some power of t minus lambda, it will annihilate whole of v. Yeah. So that tells you that the minimal polynomial has to divide t minus lambda power something. And then you want to argue that it's precisely t minus lambda power n lambda. So let's try to work this out. Yeah. So first thing to note is that so this was also a homework. So minimal polynomial of v lambda, minimal polynomial of phi restricted to v lambda has to divide minimal polynomial of phi. Yeah, so this was again because v lambda is a subspace, invariant subspace of v, phi invariant subspace of v. Yeah. Now you can just look at, you apply phi to it, then p phi of phi is 0. So that tells you that minimal polynomial must divide this polynomial. Yeah, the minimal polynomial is a polynomial with least degree, right? And we saw that any polynomial that satisfies this operator must be a multiple of it, right? When we were discussing minimal polynomial. So we know that ft divides p phi t. Also, you take a basis, you start with a basis of v lambda. You take some basis, x1 to xm. Yeah. Then, since xi's are generalized lambda eigenvector, there exists ni such that phi minus lambda I power ni xi is 0. Yeah. And then you take n to be maximum of these ni's. Then you can say you can choose a uniform n. Yeah. So phi minus lambda I power n xi will be 0 for all I. Yeah. So same n you can choose. Right. So that tells you that phi minus lambda I power n v is 0 for all v in v lambda. Yeah, because if it is true for basis elements, then any linear combination of the basis, it will be okay. Is this okay?
Yes, sir.
Yeah. So that tells you that phi minus lambda I, some power of phi minus lambda I kills the whole vector space v lambda. So that means this is the zero endomorphism. So again, the minimal polynomial has to divide this polynomial t minus lambda power n. Yeah, because when you plug in phi, you get 0. Yeah. So hence, so since ft divides this guy, and again, and it divides pt. P phi t, so it has to divide the greatest common divisor, greatest common factor, yeah, which will be t minus lambda power n lambda, right? So ft divides t minus lambda power n lambda. Okay. So n, you can take n to be bigger than n lambda. Then it is clear that ft divides something like this. Yeah. So now we'll have to also check that t minus lambda power n lambda also divides ft, and then we'll be done. Yeah. So now to finally you take a vector v such that see this is the minimal polynomial t minus lambda power n lambda gt is a minimal polynomial of phi on v. Yeah. So you can so if I decrease this factor, so if I take t minus lambda power n lambda minus 1, that's not the minimal polynomial of phi. Yeah. So if I plug in phi in that polynomial with n lambda minus 1, this is not a zero linear operator on v. Yeah, if it were a zero linear operator, that will contradict minimality of that p phi t is the minimal polynomial. So since this is not a zero linear operator, there exists v such that phi minus lambda I power n lambda minus 1 times g phi is not 0. Yeah. So you can find a vector, non-zero vector v such that this thing is non-zero. Yeah. So because p phi is the minimal polynomial. Is the statement clear? So we are just using the fact that p phi is the minimal polynomial. So if I take a polynomial of smaller degree, then and plug in phi, then it can't be the zero linear operator. Yeah. So phi is not satisfied by a polynomial of smaller degree. So we can find a vector such that it is when we plug in that vector in that linear operator, we get something non-zero. Okay. Yeah, is that okay?
Yes.
Yeah, Anarga?
Yes, sir.
Yeah, okay. Good. So now you take W to be G phi V. Yeah. So that is an element of another element of your vector space V. Yeah. Then if you apply phi minus lambda I power n minus n lambda minus 1 W, then it is non-zero because I mean this is what this follows from the previous one. Yeah. But if you apply phi minus lambda I power n lambda W, then that is of course 0 because that then you are applying the characteristic polynomial. Yeah. So the the minimal polynomial. Then because everything sense p phi is 0. Yeah. And if you apply phi minus lambda I times n lambda W, then that is same as p phi of V because W is g phi of V. Yeah. So that tells us that W has exponent precisely n lambda. Yeah. So in particular, W is a generalized lambda eigenvector. So we found a generalized lambda eigenvector such that phi minus phi. So what we showed is that phi minus lambda I power n lambda minus 1 is not the zero operator on v lambda. Yeah. So the minimal polynomial is not going to be a factor. So no smaller degree polynomial. So the factor of t minus lambda power n lambda are precisely t minus lambda power n lambda minus 1, t minus lambda power n lambda minus 2, and so on. These are the only factors, right? So we saw that no smaller degree factor will work. Yeah, will be the minimal polynomial. Hence, the minimal polynomial must be t minus lambda for n lambda. Okay. Is that fine?
Yes, sir.
Yeah. Okay, so that proves that the minimal polynomial is indeed this. So similarly, or maybe using this result, you can try to prove that this result holds even for the characteristic polynomial. Okay. Okay, so now let's just summarize the situation. So last time we proved this theorem that if V is a linear operator on V and characteristic polynomial is product of linear factors, t minus lambda 1 power m1 to t minus lambda r power mr, then we can write it as v lambda 1 plus v lambda 2 plus v lambda r, and where v lambda i's are the generalized eigenspaces, like generalized lambda eigenspaces, and and we also know that v lambda I are phi invariant subspaces of V. Yeah. So we can so this decomposition we saw last time. Yeah. So now we'll prove the Jordan form. Yeah. So the Jordan form theorem. Yeah. So let phi be a linear operator on V with this property that its characteristic polynomial of phi is product of linear factors like this. Then there exists a basis B of V such that the matrix of V is of this form. So it's block diagonal where the entries are j lambda 1 n11, j lambda 1 n1 l1. So it's double index. Yeah. So there may be many such things. Okay. For each lambda 1, there may be many Jordan terms. For each lambda 2, you'll have maybe L2. So it could be one, it could be many, yeah, depending upon how things are. So, and so on. So this is how it looks like. Well, J lambda n is a n cross n matrix of the form. So I've written it the way we were getting it. Yeah. So maybe I've written it in a lower triangular, but if you rearrange it, you can also think of it as an upper triangular. Yeah. We saw here, right? That so basically in this when we were proving this, what did we see? That we found a subspace which is phi invariant, which has this form. Yeah. Now what we'll do is we'll cook up many such subspaces which will be phi invariant, and their direct sum we will show that is whole of V lambda. Yeah. And that is how we'll work it to prove this result. Okay. So what we'll have to do is that so we will I mean, using this theorem, we already have a decomposition into phi invariant subspaces V lambda 1 to V lambda r. Yeah. So now for each V lambda 1, we'll again decompose it further into phi invariant subspaces of whose basis will be of this form, you know, generalized eigenvector of exponent n and so on. Yeah. So that is how we will go about proving it. So we will decompose this. So proving this that it is a matrix of this form is equivalent to proving that you find a decomposition of this vector space into some phi invariant subspaces, right? That is the principle we are using. Yeah. So we will find that decomposition, and that is how it will work. Okay. So any questions before I start the proof of Jordan form?
Sir, I think the meeting is again going to end in a minute.
The meeting is supposed to end in 1 minute.
That's what it says here, sir. Less than 1 minute.
Yeah. So less than 1 minute. Okay, so maybe we'll start once we'll restart this thing. Yeah. So we'll have to do it again. Okay, so I'll restart this. And so this video I'll have to keep. The first video I don't know if I'll post, but this video I'll post. And so we just, but you have anything to ask before we start the proof of Jordan form? No? Okay. Okay, then yeah, so let's just, so maybe this reduction is okay. So of course, we know that is going to be a block diagonal by the previous theorem.